Okay, today we're talking about Chapter 5, Section 7, Variation. Now normally, towards the end of the section, concepts and problems tend to get harder. I think this is actually a lot easier than what we've been doing, and hopefully you'll agree. Alrighty, so the definition of direct and inverse variation. In this section, we introduce the concept of variation. Direct and inverse variation models can show how one quantity varies in proportion to another. The definition of direct and inverse variation. So we're going to let k be some non-zero constant real number. Okay, it's very important that we allow it to happen, and we'll see that here in a minute. Then the following statements are equivalent. So just looking at just one, y varies directly as x, and y is directly proportional to x. So these two statements are equivalent to one another. All right, and if we put it in algebraic form, it's just simply y is equal to kx. Right? If we are varying directly, then we're just simply multiplying the constant. Okay, we see our constant here again. Our constant, we have to have some sort of constant. If we are varying directly, we are multiplying by the constant, right? And then obviously we're going to be dividing by the constant on number 2 here. So if y varies inversely as x and y is inversely proportional to x, then y is equal to k over x. All right, note the value of k is called the constant of variation. All right, so in both these cases, we must have a k. If we vary directly, we multiply. If we vary inversely, we divide. Okay. Normally, I keep stuff up like that up there, but we're just going to try it. We're just going to attempt to do this without that, the sandy area that we just talked about. It takes up a lot of space. All right. So, A, translate each expression to an equivalent mathematical model. So, I said A, I meant 1. All right. So now we're on A. All right. So we want to find the circumference of a circle. I'm sorry, we need to translate this. The circumference of a circle varies directly as the radius. Okay, so the circumference of a circle, we're just going to put as a c. Right, and it varies directly. So that means we're going to have a multiplication here. So we're going to have a k times something, right? Well, k times what? Well, it varies directly as the radius. So it's just simply, that looks there. It varies directly with the radius, just like that. Okay. B, so B reads at a constant temperature, the volume of gas varies inversely. Okay, so it's varied inversely. So we're going to be having that fraction. Okay, so we're going to be having, so at constant temperature, the volume of a gas. So the volume of a gas, we're going to put V is equal to, and we're varying inversely, so we're going to put the K in the numerator as the pressure. Right, and the pressure is just going to be P. And then C, the length of time of a meeting is directly proportional. So directly, again, we're going to be having our multiplication. So the length of time of a meeting, so we'll put T for time. All right, directly proportional, so we're going to put the K here, and we're just going to start multiplying. And it looks like there's not just one of them. Multiplied by the square of the number of people present. So we can put, P for people, and then the square of them. And that's it. So again, we just have to check to make sure, basically this statement here varies directly, varies inversely, directly proportional. Right? And again, we see this directly, inversely, directly proportional, inversely proportional. Well, the textbook used n for number of people, but it doesn't really matter. All right, I guess we will snip this onto it. Alrighty. So looking at the top, the definition of joint variation. Alright, so joint variation is pretty much the same thing as directly proportional, except now instead of the k times just one thing, it's going to be the k times two things essentially. Alright, so let k be a non-zero constant real number, then the following statements are equivalent. Y varies jointly as w and z. Y is jointly proportional to w and z. And that's it. We're just adding or I guess we're multiplying an extra term there. Okay. So example 2, translate each expression into an equivalent mathematical model. A, y varies jointly as u and the square root of v. So we're saying y, it varies jointly, y varies jointly as u and the square root of v. And that's it. B. And this is actually pretty cool. This is a very important very important equation in physics, and as a matter of fact, it's an equation that a lot of equations that you see in mathematics and in physics courses is built from. So the gravitational force of attraction between two planets. Okay, so we're going to say the gravitational force. So we're going to make that a. Let's put it down just a little bit. The gravitational force, put as a g. Okay, uh, varies jointly as the product of their masses. Okay, so it's going to be varies jointly as the product of their masses. And for the product of their masses, we're going to put mass 1 and mass 2. Okay, because there are two masses there. And inversely as a square the distance between them. So we would say the distance squared. Okay. So the B here was a little tricky, I guess, but if we just read it and go one at a time, then we'll be able to see, or we'd be able to get to our equation there. I'll just take up the whole page. So the applications of variation. Consider the variation model y is equal to kx and y is equal to k over x. In either case, if values for x and y are known, we can solve for k. Once k is known, we can use the variation equation to find y if x is known, or or to find x if y is known. This concept is the basis of solving many problems involving variation. Whew, holy cow. Okay, sorry about that. I guess I haven't had my coffee yet, which I haven't, but that's it. And of course, what that's saying is if we know if we have like x number of unknowns and we are given x minus 1 number of unknowns, right? So if we have 4 unknowns and we're given 3 of the unknowns, then we can solve for the fourth. And that's basically what that's saying, right? And that's what we're going to do here. Probably should have put this on another page. Maybe not. Okay, so finding a variation model. So step 1, we're going to write a general variation model that relates, honestly, the step 1, step 2, and step 3, and you're going to find this uh, as a theme in my classes. I don't really do the steps. I do the steps. I don't really teach the steps because I feel like that's just um, you've only got a limited amount of brain power right now. I know you're, especially we're getting into the middle of the semester, and it's just one less thing you have to memorize. But you're gonna do it. Okay, again, I've probably said it many times in this course, but it's like making a peanut butter and jelly sandwich. You don't necessarily have the algorithm down. You just say, okay, this is what all I need, and you get it done. And that's what we're gonna do here. So let's just begin. So the variable z varies directly as w. Okay, so this is pretty easy. So the variable z varies directly. Okay, so it's going to be directly proportional there. So varies directly as w. Okay, well I just did a. I actually did a on accident there. But yeah, there's a. Okay, and then we have solve for the constant of variation. Okay, so we need to figure out what that k is. Okay, so if we were to solve for the constant of variation, we need to isolate the k, and then we're going to be substituting in our values w, our values w and z there. Okay, so we substitute in. All right, z is 16, so we have 16 is equal to k times w, which is wait, z is 56. There we go. Okay. Um, and then we're going to solve for k. So this ends up being 56 over 16 is equal to K. Well, 56 over 16 reduces down to like 28, 8, 14, and 4, 7, and 2. So it looks like it reduces down to 7 and 2. Okay, so that's what K is. And then lastly, we are told to find the value of Z when W is 84. All right, so we figured out what K was. All right, so basically what we're doing now is plugging in K into our variation model here. So now our model becomes, and let's put Z is equal to 7 halves, because that's what K is, W. Okay, and if we want to find out what Z is when W is 84, we do Z is equal to 7 over 2 times 84, right? And let's actually get the calculator out for this one. 294. So Z is going to be equal to 294. Right? And that's it. I think these problems are a nice change of pace from mindless computation. So the speed of a racing canoe in still water varies directly as the square root of the length of the canoe. Okay, so the speed of a racing canoe. So let's just put S for speed. The speed of a racing canoe in still water, it varies directly. Okay, so we're going to have just a multiplication here. It varies directly as the square root of the length of the canoe. So square root of the length. Okay, so we're varying directly the square root of the length, and that should be good, right? Speed, square root. Okay, so A reads, if a 16-foot canoe can travel 6.2 miles per hour in water, find a variation model that relates the speed of the canoe to its length. Okay, so what's given to us is the length as well as the speed. Okay, so we need to figure this out. We need to have S is equal to 6.2, and of course we are in miles per hour, yeah. So we're in 6.2 is equal to K times the square root of the given length there, which was 16. Okay, well, the square root of 16 we know is 4, and then we need to divide both sides by 4. So we're going to end up with 6.2 divided by 4 is equal to K, which is equal to 1.5, but that's not it, so let's do 6.2 divided by 4, 1.55. Okay, so 1.55. So K is equal to 1.55. So my equation here, my equation that relates the speed of the canoe and the length of the boat is going to be S is equal to 1.55 times the square root of L. Okay, and with that equation we can solve, well, pretty much anything that gets thrown at us. And let's look at anything that gets thrown at us. And B, find the speed of a 25-foot canoe. Okay, well, we have the speed is equal to 1.55 times the square root of 25. Okay, well, square root of 25 is 5. 5 times 1.55 is about 7.5 something. 7.75. Okay, so 7.75. And that's the speed. Did I put B on that? 1 second. Okay, I did. Good, good, good. Okay, so now we're going to talk about the loudness of a speaker. The loudness of sound measured in decibels varies inversely. So loudness we'll put as L. So the loudness of sound varies inversely, so we say we're going to be division, so inversely as a square of the distance between the listener and the source of the sound. Okay, so we just say varies inversely there of the distance. Let's fix that D up a little bit. Here we go. Just make sure. So loudness of, let's see, the loudness of a sound measured in decibels varies inversely, so we're doing division, varies inversely as the square of the distance between the listener and source sound. Okay, so that's it. Okay, good. So if the loudness of sound is 17.92 decibels, okay, so 17.92 decibels at a distance of 10 feet from the speaker. So again, in all these cases, what we're doing to solve these application problems is we have to figure out what that constant is. So we're given everything but the constant to figure out. Okay. So if we solve this, we know that this turns into 17.92 divided by, well, 10 squared is 100, so we just put a 100 there, is equal to k. And again, in this particular case, we divide both sides with 10 squared. So we're trying to figure out what k is. Um, that did not sound right, and that's because I did my arithmetic so wrong there. It should be 17.92 times 100. Sorry about that. Is equal to k. Yeah. Now this should be a lot easier. 1792. Okay. So k is equal to 1792. Right. So we got what k is. Now, actually, I should put that in blue. Now we're on to this. So what is a decibel level 20 feet from the speaker? Okay, so we need to figure out what that would be, but we're told already, we found what k is equal to, so we're going to have L is equal to 1792 all over, and 20 feet from the speaker, so it would be 20 squared. Well, 20 squared is 400, so we'll put 400 there. And 1792 divided by 400 is 4.48. 4.48 decibels. Okay. And lastly, we have Hurricane Katrina, which I read that this latest hurricane that went through, or Irma or something, I forget what was the name, um, was just as bad as Katrina. That's awful. And I think it was almost to the day as well, August 29th. So, in the early morning hours of August 29, 2005, Hurricane Katrina plowed into the Gulf Coast of the United States, bringing unprecedented destruction to southern Louisiana, Mississippi, and Alabama. The winds of a hurricane are strong enough to send a piece of plywood through a tree. And we have their picture there. So the kinetic energy of an object. Okay, so this is our equation we need to start off with. The kinetic energy of an object. So we're going to say the kinetic energy. We'll do E for energy of an object varies directly. Okay, so we're going to have a multiplication here. So varies directly. Varies jointly as the weight of an object at sea level. So W and the square of its velocity. So V squared. Let me make sure I read that right. The kinetic energy of an object varies jointly at. All right, so if it varies jointly, we know that's multiplication as the weight of an object, which is W, at sea level and the square of its velocity, which we have here. Okay, so we have to figure out what K is now. So we're going to be given everything but K, and we have to figure out what K is. So here we go. During a hurricane, a 0.5 to 1 pound stone traveling at 60 miles per hour has 81 joules of energy. So my energy is 81. Okay, we're trying to figure out what K is here. Right. Um, the weight is 0.5 to 1. Okay, so how 0.5, 0.5, I don't know, let's do 0.5. Okay, so during again, so the weight is 0.5, and it is traveling at 60 miles per hour, so we're going to have 60 squared. Okay. So if we solved all this for k, this would end up being, just the equation is going to be 0.5 times 60 squared all under 81, and that's equal to k. Okay, all I did was just all I did was move everything to the left and isolated the k there. All right, so we should have, let's do the arithmetic here. So 0.045. So k is equal to 0.045. Okay. Now my new equation is going to be my kinetic energy, which is equal to 0.045 times the weight times the velocity squared. Okay. So now that we figured out what k is, we can proceed with the rest of the problem. Suppose the wind speed doubles to 120 miles per hour. Find the kinetic energy. Okay. So my weight apparently stays the same. So we'll have my kinetic energy is equal to 0.045. My weight stays the same at 0.5, but my velocity doubles to 120. So we would say 120 squared. Okay, so we can just do this arithmetic. Okay, so 324 joules of energy. Right. Now that doesn't mean much to you or I because we don't really have any context. But if we were to have some context, here's the context of what that is. Because of the variation model we have here, okay, where energy is directly proportional to the weight and the velocity squared. Well, at 60 miles per hour, we had, what was it, 81 joules? Yeah, 81 joules of energy at 81 miles per hour. But when we doubled the speed, I'm sorry, 81 joules of energy at 60 miles per hour. But when we doubled the speed, our energy uh, uh, quadrupled, right? So we doubled the speed, but our energy quadrupled. So that just shows the variation of that. Does that conclude today's lecture?